Well, good afternoon, folks. I'm very excited to be here presenting our work. This is a joint work in between University of Massachusetts Lowell and Intel Corporation at Hudson, Massachusetts. The topic today is BMAC, accelerating P4-based data plane with DPDK. I'm Peilong Li from UMass Lowell. Also on the UMass Lowell side, we have Xiaoban Wu, Yan Luo. And Intel folks include Larry Wan, Mark Papping, Atu Quatra, and John Morgan. All right, so this is an agenda here for my talk. I'm going to first introduce the background of P4 language and the P4 behavior model version 2. And then I'll state the problems of current behavior model and then our design motivations. After that, I'll go through the design overview of BMAC and the optimizations we have done on BMAC. And later, we have the performance evaluation, a couple of slides, and finally, the future directions and conclusion. All right, to begin with, I would like to have a quick review survey here. Please raise your hand. How many of you are familiar with P4, or at least understanding some basics? Thank you. And how many of you here think P4 is just another alien language you will never touch? Okay, thank you. The good news is P4 is much simpler than the alien languages. It has simple semantics and two major advantages. First, it is protocol agnostic, meaning the programmers can have their customizable headers and their own customized data plane functions. And second, it is hardware agnostic. P4 package comes with this front-end parser, the compiler. But it's up to the hardware vendor to design their back-end compiler to support their target. This diagram shows exactly what I just said. The target can include like software switches, programmable hardware switches, NPUs, FPGAs, you name it. So P4 behavior model is just a target that runs like a software switch. People used to have behavior model version 1, which is now deprecated because it requires recompilation for every single P4 program. Now people use BMV2, which is a static executable that consists of some very basic building blocks like parser, deparser, match-act tables. And this BMV2 can be configured by your P4 program. Let's say, take a P4 program and apply the compiler provided called P4CBM, and that will generate the JSON configuration file. And by using the JSON file, you can finally configure your program onto this static BMV2. Now, there's a big problem in behavior model version 2, which is exactly indicated by its name. It is a great software switch, but it can only be used to verify the behavior of a P4 program, which means as a software switch, it has very poor performance. According to our experiment, almost all packets will be dropped if we run a small package on 10G link. There are a couple of reasons behind that. Just name a few. If you look at this diagram, there are 4 major steps included in the BMV2 code base. That is initialization, receiving, processing, and transmitting. OK, so on the receiving side, it uses libpcam, which is a well-known library that is kind of slow in some cases. And also Linux NIC driver on the receiving side. Also, it only supports single-threaded processing, no multiple RxQs. That means no RSS support. Also, there are all kinds of unnecessary memory copies all over the place in the code base. So with that, we are motivated to design an accelerated version called BMAC for P4 programs. It is not like it's not like a P4 compiler as presented by the existing works, PCs or P4-LT. It is a P4 target that is designed on a multi-port platform. You can use it as a substitute for BMV2, but with line rate performance. Behind this, the magic behind this is the performance acceleration, such that we leverages the DPDK libraries and DMD drivers for faster packet I/O. We apply multiple optimizations, which I will discuss in greater details later on, to such that reduced memory copy, multi-threading using parallel SSE instructions, etc. And we want it to be transparent to P4 programs such that it can support all P4 programs and all DPDK compatible platforms. Also, a great advantage of using BMV2 is we are not requiring the P4 source code. You can just pass me the configuration file generated by your P4 code, and I can configure the BMAC switch. So with that, I'd like to introduce BMAC as an overview here. And there are three major optimizations I want to run through. The first optimization is this, okay? So we first change all libpcam related functions in BMV2 to DPDK functions. And then we change Linux drivers to PMD driver. Also, we incorporate RSS functionalities into our code base so that we can support multiple queues and multi-threading. This is optimization 1. Optimization 2, we focus on this block. We remove redundant memory copies in the receive function existing in BMV2. Okay, so for BMV2, for each incoming packet, it will create a space for it, and that space will later on be copied over to the pipeline stage. So in between, this is a redundant stage because of using libpcam. By using mempool in DPDK, we can eliminate that. Secondly, we want to remove mutags for each parsed header. So in BMV2, for each parsed header, they have a mutags applied on it so that if there are multiple threads you want to use that parsed header, they won't have conflict. So we do pre-allocation for each worker node so that we can remove this mutags mechanism. And the third optimization we did is on this processing block. Okay, so we changed the original P4 LPM into DPDK LPM, and we leverages those SSE parallel instructions that is used by DPDK. So to evaluate our design, we set up this test environment. We have 2 Intel Supermicro servers. On each server, we have 2 NIC cards connected back to back. Okay? On your left-hand side, that's the SM1, which runs the DPDK package in. The TXN generate 10 gigabits per second traffic with random destination IP. And on the RxN, we count the received packets. On the right-hand side, SM2, we run the BMV2 simple router target on it. It simply works as a router that contains a lookup table, checks your incoming packets with rules. If there's a match, then I forward. If there's no match, then I drop. Okay? So now I have a couple of slices I want to run through to evaluate the performance. Firstly, I want to show the hardware performance of our platform. So firstly, the NIC card transmission capability. For the TXN, we always send 64 million packets with this number of distinct flows. Okay? So in the table, as you can see, for across all size of packet size, we can reach almost 10 gigabits per second framing rate. Okay? That means the TXN works fine. And for the RX end, it only receives packets and then drops. So we just want to validate the receiving capability. And there's no transmission to the output. So this figure down there shows that for large size, mid-size, and small size packets, we can always reach almost 99% of packet receiving rate. Okay, that is nice. So now let's look at the performance comparison between the vanilla BMV2 versus the optimized version BMAC. Okay? So because vanilla BMV2 can only support single thread, that's why all this test in this diagram is showing on single core. Okay? That's why it's kind of poor in performance. So as you can see on this diagram, x-axis, we have different size of packets, from large size, mid-size, to small size. And for each packet size group, we have the original version, the vanilla version, PCAM version, versus the BMAC version with optimization 1. Okay? And the BMAC version with optimization 1 and 2. And finally, the BMAC version with all three kinds of optimizations. So there are three key observations here I write on the right-hand side. We can see within each packet size group, almost all DPDK versions outperforms the original PCAM version. And the more optimization that we apply to it, the higher performance we can gain. Okay? If you look at the blue bars and the orange bars, they are almost the same and a little bit down on the orange bar. This is because we are only running single core. Okay? DPDK is not showing any advantages on the single core. Okay? It maybe has some overhead on it. Now, it's more interesting to see the performance on multiple cores, since the major advantage of using RSS and multi-queue is running parallel execution. Okay? You may notice that PCAM is not on this chart because it's not, obviously it's not supporting multi-core. So the performance is compared between optimization 1, optimization 1 and 2, and optimization 1, 2, 3. Three key observations here. There are 3 times, 5.5 times, and 23 times increase of performance on the large, mid-size, and small-size packets if comparing to the original single-core version of BMV2. And we can also reach line rate for large and mid-sized packets with all 3 optimizations. The only anomaly here is a small packets. You may ask why this small packet cannot reach the same high performance as large and mid-sized packets. Let's dig into the reason why. In this test, we want to figure out the performance scalar for small packets. So in the P4 processing code base, we divide the code base into 5 stages, okay? From receiving to parser to the pipeline processing to deparser and transmission. And we gradually add stages to the pipeline so that we can find the biggest performance drop. okay? And in this experiment, we run 4 cores with the small size package. So as I said, if you look at the x-axis on this diagram, the first column, the first bar, contains only a single pipeline stage, that is Rx. And the result of packet receiving rate shows that it can almost reach 100%, which is consistent with our previous Rx verification case. Now, if you look at the second bar here, there's a 20% performance drop. This is because we add Tx to the whole pipeline. Now, this whole pipeline contains both Rx and Tx. And in this case, it is very similar to the DPDK L3 forwarding use case, okay? And also, this performance data, 80%, is consistent with the reported NIC card performance, okay? So we are good here. Now, the biggest drop happened when we applied the parser stage into this pipeline. This is because we dig into the code and find for each incoming packet into BMV2, BMV2 will use the new object, for object-oriented language, the new object for each package. This is the most time-consuming stage inside of this entire pipeline. And this incurs like almost 60% of performance drop. So here we can understand that there's a trade-off, right? If you want to have the flexibility of using P4 in your Dataplane function, you want to apply the parser because the flexibility comes from the parser. But if you apply the parser to it, then you lost the performance. So there's a trade-off. The question now is there a way that we can retain this flexibility while we increase the performance? The answer is yes, but it's not covered in this work. I'll state that in the future work. The fifth test is about the performance with various number of cores. In this case, we take the optimization 1, 2, 3 case because it's the most optimized version. So for large packets on the first group, you can see we can reach the line rate with 4 cores. For mid-sized packets, we can reach line rate with 8 cores. Okay? It is not shown here, but the results are consistent with optimization 1 and optimization 1 and 2. Okay. And lastly, how about we change the P4 LPM into the DPDK LPM? So for P4, it leverages the Judy library, which is used to creating and accessing dynamic arrays. Okay? For us, we want to change the Judy library into DPDK LPM library, which leverages SSE instructions, and also is very cache-friendly in the code design. We can find that it's not very evident, but if you look into greater details, the DPDK LPM is slightly better for all cases. And DPDK LPM performance benefit is more evident when the root size is small, okay? So the root size changed from 10 to 100 to 1,000, and it's more evident on the small root size. This is because the overhead of Judy library. So finally, I want to conclude with the 4 bullets here. The DPDK accelerated behavior model reaches 10 gigabits line rate for mid and large size packets and yields 23 times performance boost on the small packets. As I mentioned before, to address the parser impact on the P4, on the small packet, we need to do some techniques like pre-allocation. So instead of new object every time, we want to pre-allocate a memory space so that we can reuse. We don't need to new over and over again, we can just use the same space. We can read that if the packet is gone, and then we reuse this memory space. This can be a solution for this, and we are currently working on this, and hopefully we can get better results. And then we propose the multiple practical optimizations on BMV2, which are instrumental to all P4-based data plane designs on multiple platforms. We conduct in-depth performance study on the proposed BMAC system from the architecture and software perspectives. With that, thanks for your attention, and I would like to take questions from the audience. Okay. I'll be on offline. Yeah, I can talk offline.